now we'll look into ventilation and ventilation we finished. We'll look into noise and some fundamentals of acoustics, noise control, design for good listening, and insulation. This is how we'll divide them. So essentially, if you see, basically what is noise? Unwanted sound. Noise is basically unwanted sound, and good listening was there for a very long time, prehistoric times, because open amphitheaters or the Greeks dramas, or even in say Gupta age Shudraka, you would have heard of Shudraka, Vishakdatta, Navratna in Vikramaditya's Shudraka has Mrichakatikam. I don't know whether you have seen. There's a Hindi movie based on that Utsav, but Habib Tanvir made a very good Chhattisgarhi drama out of it, Mitti Ki Gadi, Mrichakatikam. So you see, the dramas were there, plays were there, dances in Indian, Bharat Natya Shastram. So all the dances actually originates, Indian classical dances originate from there. So these were there, good listening, good performance, these were very much there, but noise is a recent phenomenon. You see, so therefore there are places like temple dances, or as I said, dramas during the Gupta age in India, or romance, in similar time. But obviously scientific knowledge is relatively recent, and noise is a recent development, because noise essentially we treat it as a pollution. It's unwanted sound, we don't want them, and it largely has come from industrialization, industrial revolution, advent of vehicular traffic, and then various kind of mechanization that would have gone in associated with. So noise can, that's right, so that's what it is. Now noise can prevent people from performing at their maximum capability. You're disturbed, it's actually annoying at times, there's a discomfort, and can even be damaging to the health if it is a long term exposure, right. So that's what it is. Thus, since it's unwanted sound, therefore it deals with sound, and of course sound is perception of certain quality of mechanical vibration in air. Like we have sensory mechanism, we have been looking into thermal, the skin can feel the temperature, right. Visual, of course, the eye is a sensory mechanism. Similarly, certain type of mechanical vibration in the atmosphere or air around the ear, that's we can perceive. So sound is a perception of certain quality of mechanical vibration propagating through air by, we perceive through our human ear, that's the sensory organ. Thus sound and hence noise requires source for its generation, because it's a mechanical vibration, so you have to have some kind of a source that should generate, and then obviously mechanical vibration essentially transmit by motion of the particle about the mean position of equilibrium. Mechanical vibration you are talking of, not electric field or magnetic field, electromagnetic radiations. So therefore you need a medium where particulate medium which can, where through which energy can be transmitted through motion of those particles about their mean position of equilibrium. So this is usually air, which is just close to our ear, and receiver is the human ear. So that's what it is. So sound is transmitted through the medium air and is perceived by human ear, sensory sensory organ. So I have to have a source. A simple source could be like a strip, like this is a strip which I can just pull on one side and release. So when I pull on one side, I actually create a kind of a compression of the air there, because air was at equilibrium. I just pull that strip and I create a compression. But I have pulled it, the moment I release it, it will have a tendency to go back to its original state. So, that is here. So, then it moves there, this strip, like a scale or something, like a steel plate, steel strip you can think of, you just pull it and just release it. So, since you have given some energy, it will have a tendency to go back to its original state, but it goes further beyond, and air here is compressed, and when it goes back more than its original position, there is a kind of partial vacuum created. So, this is how this is the partial vacuum, then there is a compression. Then if there is it goes to the extremity and again tends to return. When it returns, when it goes to the extremity, of course, there is compression created on the other side. When it returns, there is a vacuum on the other side, and when it comes back again here, supposing it is moving sufficient displacement I have given in the beginning, then it moves. So, again it will compress, first compression, then there is a kind of vacuum created because it has gone to the other side. When it comes back again, it will create again another compression, and then again and by this time, since this is already compressed and this air is not compressed, air here is not compressed. So, this compression will have a tendency to cause the air to spread. In other words, the compression will have a tendency to move when the next compression comes. So, it is actually trains of compression, then what we call rarefaction or partial vacuum. So, I will have something like this, the first compression, then there is a vacuum, and again it came back, another compression created, then a partial vacuum, and if it continues to move in this manner, vibrate about its mean position of equilibrium, then it will create a kind of compression also on the other side as well, but I am showing only one direction, one side. So, this is the direction of the movement of this compression and rarefaction. In other words, particle will start moving, air particle will start moving about their mean position of equilibrium, they come close to each other and then they separate out, right, and it induces some similar kind of motion to the next set of air particle, and when again another compression comes, this pushes them apart. So, this trains of compression and rarefaction that travels, and that is what is sound. We understand, maybe you have done the same thing in school. So, that is what is sound, and that is how this particulate motion, when it comes and hits our eardrum, there is a sensory mechanism which has got a diaphragm, eardrum. I will have a simple diagram there, and this energy, this motion, this energy, you can perceive it in certain manner through certain transmission mechanism from eardrum to the brain, and brain perceives this motion, and that is what we hear them as sound, or distinct one sound from another. So, if I look at it along some space direction, x direction, there will be negative pressure and positive pressure, because compression and there is a partial vacuum. So, these pressures would actually keep on, I can assume that it is periodic, because first I had a compression, then there is some vacuum, and then there is again compression, but it is not stepped, it would increase gradually and then decrease gradually pressure from compression. So, therefore, I can think in terms of this kind of a periodic one, because the compression would repeat itself after a certain period of time. So, we can think in terms of the pressure variation over and above atmospheric pressure, superimposed over atmospheric pressure, right. Sound pressure is superimposed over atmospheric pressure. So, if I write pressure P, this is amplitude of pressure, we generally assume them to be sinusoidal or cosinusoidal, and I can actually sum them up. If there is any other periodic one also, I can break it up into number of sinusoidal or cosinusoidal, as we have done it earlier for temperature wave. So, therefore, we can assume a pure tone or pure single frequency only or single periodicity. So, when it repeats itself, the pressure peak and pressure starts from 0. Initially it was at 0 when I have given full displacement, pressure was 0, right, and when I release there is a compression. So, pressure so it increases, pressure increases, then decreases, and so on. So, from 0 pressure to again 0 pressure, this is what we call as the time period. Same thing we did for temperature, 24-hourly period we said, when the temperature repeats itself, here the pressure repeats itself. So, this to this is the time period, this to this is the time period, right. So, time period is nothing but, since we express them, we can express this pressure in terms of time, and we are saying that it is periodic, repeats itself after certain period of time. You can express periodic sine functions we know are periodic. So, you can write it like some amplitude Pa plus some sine omega t plus phi, right. So, that means when t is equals to 0, it is equals to p sine phi, right. If this is the case, when t is equals to 0, Pa or to the omega t is equals to 0, so sine phi, so Pa sine phi at t equals to 0. In my case, if I take it equals to 0, if I take it to be equals to 0, then in this case phi is equals to 0. But supposing the wave would have started somewhere from there, my datum is somewhere there, right, then I would have had some value of phi. So, that this phi defines the starting point, because at t equals to 0 where it was, t equals to 0 where what was the value of the pressure, and Pa is the pressure amplitude. So, at this point, if phi is equals to 0, at t equals to omega t equals to pi by 2, omega t equals to pi by 2, I will have Pa, because sine pi by 2 is equals to 1. So, this will be equals to Pa. Now, period is, so therefore, it repeats itself after t period, and this can be because sine function repeats 2 pi, sine function repeats itself after 2 pi. So, I can write exactly the way we did 2 pi over omega, or we call it, since it is time, the number of such periods in unit time, I call it frequency. So, unit time, how many periods? That would be 1 by t, f is equals to 1 by t, that we know, because t is the time for one repetition, 1 by t is the number of repetition per unit time. So, t is and during this period of time, the sine function has gone from twice pi. So, angular frequency is omega. So, twice pi, you can write it as twice pi by twice pi f. Twice pi f is equals to t, because omega is the angular frequency. So, this is how we can just express pressure. We can express pressure. This is how we can express pressure, right. You can express pressure in this manner. Express pressure in this manner, right, sine omega t plus phi. And if it has moved, if the wave has moved through a distance x, right, through a distance x or delta x, let me call it, it has moved through a distance delta x during some period, some time delta t, then wave velocity will be given as delta x divided by delta t. The wave has moved delta x divided by delta t, right. So, c is equals to wave velocity, we denote by c, velocity of the wave, not particle. Particle, this peak, how much the peak has moved over a period of time of delta t, that is delta x, let us say. So, delta x by delta t, and delta x is simply, this I call as wavelength, that is the distance from this point to, or maybe distance from this point, this point, or it is written here, yeah. So, when distance it travels, the wave travels during one time period, or from same repeats itself, the distance after which it repeats itself, for example, a compression to compression, compression peak to compression peak, this distance, because as I said, it moves as a train of pulses. So, this distance, compression to compression peak, that I call as wavelength, and during this period, during this distance, how much time it would take during this travelling from this point to this point? It is t, time period, because same time when this wave has moved at this position, by this time here again the 0 pressure would have come back, right. So, lambda by t. So, simply c is equals to lambda into f, because 1 by t is equals to f. So, this you must be knowing. So, for velocity, wave velocity is equals to frequency multiplied by the wavelength. So, we define wavelength in this manner, time period in this manner. So, we consider plane wave. for simplicity, most of our cases we can treat with the plane wave, which is, so basically this is what we call simple harmonic motion, repeats itself, it's periodic, repeats itself after t time period, and by the time it travels to a distance lambda during the t period. So this is what we call a simple harmonic motion, right? And you see, what about the particle displacement? Let me denote particle displacement by y. Particle displacement y. Y is particle displacement, right? So when time was 0, right, I have already given a displacement at time 0 because I have given a displacement and released it. So it actually went to its maximum displacement at time equals to 0. So then it should be a cos function, because cos 0 is equals to maximum, 1. So y is equals to y0 cos omega t. So if I am defining pressure as Pa sin omega t, right, the displacement will be y into y0. Y0 is the maximum displacement or amplitude of displacement. Y0 is the amplitude of displacement. So particle contact with the source will also vibrate as the source. So I gave the source this displacement. So particle that's very close to the source will also vibrate with the source itself. Same diagram earlier, I had this one. So if this moves somewhere there, the particle close to this one would have moved together with the source itself. So it would have had the same displacement as the source, and then displacement of particle at a distance x from the source will then, the particle which actually was, particle movement has started from the source. Source initiated the particle movement. So the particle starts moving from the source, then it travels, because as when it goes back, there is a rarefaction, and then again another compression comes in. So in the process, this particle movement about their mean position of equilibrium, they start moving. So the movement of the particle some x distance away, it would have been initiated t times earlier at the source. It would have been initiated t times earlier at the source. The train of pulses moves. So first compression, it would have triggered off a compression later on and another compression later on. So the one compression at some distance x, it would have been actually initiated at some t times earlier, right? So x divided by t is actually c. If it had been started, x divided by it would not, so x at x distance, so it would have been initiated some, let's say, t times earlier, and x divided by t is nothing but c. So x divided, so what we can say is t dash time. Here we are saying the t dash time earlier because t is my general notation for time. So therefore its nature of the wave or quality, the amplitude of the particle will be given by y cos omega t minus omega t dash, because it started t dash time earlier. It started t dash time earlier, not lag by. So it will actually start at t dash time earlier. So the form or the point or value of the particle displacement will be simply yt at t equals to at current time, t yt at current time minus y omega t dash, right? And t dash is nothing but x by t dash is equals to c. So I can relate this to c. Let us do that. So y x t, particle displacement at any point, will be given as y0 cos omega t minus omega x dash x by c, because t dash is nothing but x divided by c. So omega I can take it out, and if I take omega out, or I can write twice pi f, both I can write twice pi f. I can write it like this. So this is written as kf. C is equals to lambda f, omega is replaced by twice pi f, and this is written as k, which is nothing but twice pi by lambda. So it is written like this, omega t minus kx, because it is a function of x, and k is twice pi by lambda, and it is called wave number. Twice pi by lambda, which is equals to omega by c, because twice pi by lambda, so it can be twice pi by lambda, and if I write it like this, twice pi f, c was lambda into f, c was both twice pi f by twice pi f. So, this is equals to c, this is omega. So, I can write as omega by c. So, wave number is k. So, the equation for particle displacement is omega t minus kx. It is just, maybe you have done some of this earlier, but it is a repetition since we are looking at noise, some fundamentals which are required. So, it is a plane wave travelling, right. It is not spherical waveform, plane wave travelling in one direction, that is why x direction only we are taking, and this is what it is. So, velocity will be what? Velocity will be derivative of this one dy dt, rate of change of, because particle moves to its extreme position, come back to its 0 state, or I mean x equals to 0 or y equals to y0, and that at starting point, and then again it goes back towards minus y0. So, y0 to y0, and when it goes to the extreme end, the velocity was 0. It starts, acquires certain velocity at the central point, and then because of its inertia travels further to minus y0, where the velocity becomes 0, and then it tries to come back and so on. Because the stiffness of the system, it would resist the, if you were given a kind of displacement to it, it's the system itself will resist that kind of a displacement. So, it will try to come back to its original state. In the process, from 0 to velocity becomes somewhere maximum, and then it tends to again go back to 0, and so on and so forth. So, velocity is again function of sine function, same as the pressure. Velocity and pressure, they are both sine function, while displacement is cos function. In other words, I can say that velocity and there is velocity and pressure, they are both sinusoidal or varies together, and differentiating y equals to y0 cos omega t minus x with time will give me a omega multiplied sine, minus sine will come sine. So, it is opposite direction as a displacement. If it is moving along this direction, the velocity would reduce. When it has gone to extremity displacement, it is maximum, velocity is 0. That is what this is saying, right. So, uxt is equals to, then I can write it like this, yeah. No, if you go back to this, if you go back to this states, if you go back to this state, maximum displacement at t equals to 0. So, cos 0 is equals to 1 multiplied by y0. So, you see, this is what it is. Maximum displacement is y is equals to 0. That is why, right. So, anyway, coming back to the same thing. So, this is u, I can write it like this, u is equals to uxt, and u0, now u0 will be simply minus omega y0, and sine omega t, because if it is minus, I can put it as pi, right, because sine pi would make it minus. So, omega t minus kx, sine remains same, only this minus sign I have written like this. So, u is equals to y0. You can see that actually this has got a pi phase difference, right, pi phase difference with pressure, with phase difference with So, anyway, this is a phase angle I can put in, and I can write u0 is equals to omega y0, right. Okay, amplitude of velocity is u0. So, velocity amplitude is u0, and displacement are out of phase by 90 degree. So, they are, one is sine, another is cos, and one is sine, another is cos, right. If I differentiate it again y, what will I get? I will get acceleration. So, it will yield actually acceleration. So, this will become, this minus sign remains, it will become omega square, and it will become cos omega t minus kx again, right. So, acceleration is given by this, velocity is given by this, and amplitude of acceleration will be somewhere there. So, that means what? Acceleration and displacement, when acceleration is equals to 0, displacement is also equals to 0, and that means when I have taken it here, it will tend to accelerate at a very fast rate from 0 velocity to a higher velocity. And when it comes back to its starting, I mean original point from where I have pulled it, it will actually show acceleration equals to 0, velocity at its maximum, because it will cut it down. Now we have to try to reduce it down. Anyway, so this we can understand. So from this we can get some idea about the wave equation, and we will try to look into it, because there is some relevance of this one, although we are not solving the wave equation. But if you are interested in further conceptual understanding or certain things later on, you have to solve wave equation somewhere, for example transmission loss through layered wall and so on. Although we will not use it much, but I will derive it to define something called acoustic impedance. So we need to derive it for the purpose of understanding what is called acoustic impedance. So if I differentiate, we have differentiated twice, got acceleration. I can differentiating twice with respect to x. What do I get? I have differentiated with time to get the acceleration, but y is a function of x and t. So therefore I can differentiate twice with x also. So if I differentiate twice with x, that would result in k coming in here. First it was y0 cos omega t minus kx, right. So sine would have become minus, and there is a minus, it would have been plus, right. But second time when I differentiate, the minus will come again back here, because originally it was cos omega t minus kx. If I differentiate with respect to x, I will get minus k sine omega t minus kx. Dy dx would be simply minus k will come, right, because I am I am multiplying by minus k, and then when I minus plus minus, this will come plus actually, because sine cos, if you integrate cos, what do you get? Minus sine or sine, and then second time I do it, there will be a minus. So that is how the minus k square comes in, k square cos, right. So you can see this is same in both the cases, and so is y0, this is also same. So if I take ratio of these two, what will I get? If I take ratio of these two, if I take ratio of these two, d2y dx square and ratio of t square y dt square, by this if I take it, these terms will cancel out and I will be left with how much, what was this term, omega square, right. In case of this one it was omega square, so I will be left with omega square by k square, omega square by k square. And what is k? We defined it as omega by c, wave number. So omega square, so this comes out to be, this comes out to be equals to this, right. So you see, this is what it is, this is what the wave equation is. This is what is called wave equation in one dimension. This is what is wave equation in one dimension. But if I repeat this process for p, I will get same thing. P only thing was, it was now starting with sine, and if you twice differentiate, sine will again come back, and velocity also same thing. So therefore this twice differentiate with time and twice differentiate with x. So the nature of the equation, as you can see, earlier we had heat transfer, this was dt d temperature field variable was my temperature, and temperature was simply, it was a parabolic equation. This is not parabolic, this is actually wave equation is hyperbolic. This is hyperbolic, not elliptic, hyperbolic equation. I think it is hyperbolic differential, PDE, partial differential equation. So any questions we will answer, then we will follow from